Hello students, in this lecture we will deal with module 3 of engineering physics for Bachelor of Engineering semester 2 of ITU Belagavi. We will start with Maxwell's equations and later proceed to electromagnetic waves. In our institute we have done the course outcome in such a way that this third module comes as CO2. At the end of the course, student will be able to realize the interrelation between time-varying electric field and magnetic field, the transverse nature of electromagnetic waves and their role in optical fiber communication. So as a syllabus in Maxwell's equations, we have to learn about fundamentals of vector calculus, divergence and curl of electric field and magnetic field, Gauss divergence theorem and Stokes theorem, description of laws of electrostatics, magnetism and Faraday's law of EMI, that is electromagnetic induction, current density and equation of continuity, displacement current with a derivation, Maxwell's equations in vacuum. Further going to electromagnetic waves, the wave equation in differential forms in free space. There is a derivation of equation, the wave equation using Maxwell's equations. Plain electromagnetic waves in vacuum, their transverse nature, polarization of electromagnetic waves, a qualitative approach. To start with, you need to know about the fundamentals of vector calculus, del operation, gradient, divergence, that is del dot a vector, curl, that is del cross a vector, and some integrals like line integral, surface integral, and volume integral, which you have studied in mathematics as well as in the introductory physics class. Before going further, let us look into the important milestones which in fact led to the Maxwell's equations. As you know, the inverse square law was, let us begin from then. Inverse square law was invented by Charles Coulomb in 1785 and Oersted, who first to notice that deflection of compass needle when placed in a circuit carrying electric current. In 1820, Felix Savart and Baptiste Boyot they invented a method to calculate magnetic field around a current carrying conductor, which later known as the Biot-Savart law. 1826, Ampere, Andre Marie Ampere, invented the relation that is del cross H is equal to J. It means that the curl of magnetic field is equal to the electric current density. There you could see already the relation between magnetic and current parameter, electric parameter. In 1831, Michael Faraday and Joseph Henry independently, in fact, showed that an EMF can be induced in a circuit by a changing magnetic flux. 1832, John Curl F. Gauss, electrostatic and electrodynamical laws, including Gauss law. In 1861, James Clerk Maxwell formulates the laws of electromagnetism. He forms the Maxwell's equation and then later continues to theory of electromagnetism. And in 1887, Heinrich Hertz in fact demonstrated the electromagnetic waves and generated also it in the laboratory. Let us begin the theories one by one. To start with, let us see the Gauss law in electrostatics. So here, consider a surface, a Gaussian surface. This is entirely is a Gaussian surface, as you could see. And in this Gaussian surface, what we say is nothing but a paper, you can imagine, wrapped into an irregular shape, and the volume is within that, and it is included by the surface is nothing but the paper itself. Okay. Now within this Gaussian surface, such a Gaussian surface, you consider one charge, that is Q1, and from the charge the field is getting diverged, and consider this line as a diverging line, and that is a field line that is passes through the Gaussian surface, this is a Gaussian surface, and moves out. Okay, so this surface, let us consider as the surface area as ds, and then you could see that in the surface area ds, the line that is passing, that is flux density d, is passing at ds. Then it can be shown that the total electric flux over the entire surface as a surface integral, and that is nothing but psi is equal to surface integral of d dot ds, and gives nothing but the charge q1. If we consider the charges q, q2, q3, q3, q4, etc. like this, qn, within the surface area, then total charge q, that is capital Q I am representing here as capital Q, can be represented as sigma q, that is the summation. Then psi will be equal to the surface integral itself, that is for the sigma q, that is for the entire one, for the collection of charges, which is nothing but on the right hand side you can replace that sigma q as just capital Q. So that means what happens? That means we have psi is equal to q. That means total flux, read the statement here, total flux over the entire surface is equal to the total charges enclosed within the surface. It's a very simple truth. Let me begin that. Total flux over the entire surface is equal to the total charges enclosed within the surface. That's all. Okay, and that is nothing but the Gauss law in electrostatics. Let us move to the second law, which is again by Gauss, which is known as Gauss law in magnetic fields. Is nothing but Maxwell's equation in magnetostatics, which in fact gives another Maxwell's equation, that is Maxwell's second equation. Okay, here again consider a closed surface similar to the previous one, and then we consider that the flux line in any surface which will enter is going to exit from another point. So that means here also you could see that the flux that is entering here is going to exit out. This is something similar to, as you could imagine, the bar magnets wherein you might have studied in elementary schools, that flux lines are traveling from north to south making a loop. So that is similar to the case what we speak here. So which means what? Which is nothing but total outward flux is equal to total inward flux. Okay, so that means total outward flux at that location is equal to total inward flux. That means whatever is entered is going to exit. Then divergence, if you consider, that is going to be 0. Divergence will be 0. So mathematically, if you are writing that, that means divergence of what? Divergence of B. Divergence of B is nothing but the magnetic field. So divergence of B, that is del dot B vector, is equal to 0, is another Maxwell equation, that is Maxwell equation 2. After two laws by Gauss, let us move further for another interesting law by Ampere. Why it is interesting? Because in the case of Gauss, as you could see, there were two laws. One was dealing with electricity and other was dealing with magnetism. But here in Ampere, we have the relation between electricity and magnetism. Fine. Now, let us consider this coordinate system. Let us consider this coordinate system. And I'll consider coordinate there, magnetic field H vector. Let us consider this magnetic field H vector, the three-dimensional coordinate system emerging from the point P. Emerging from this point P. Let us imagine a rectangular loop ABCD parallel to XY plane. You need to imagine this. You need to imagine this. This is the XY plane. This is XY plane. So consider a rectangular loop ABCD parallel to XY plane as the curl of the magnetic field around P. JZ, consider some JZ and AZ cap with the current density and unit vector respectively along Z direction. Along the Z direction. Like this. Then components of curl of magnetic field can be shown as curl of magnetic field. Okay, curl of magnetic field can be shown as like this. Mathematically, curl H, where it is in XY plane. It is in XY plane, is equal to JZ AZ. Now you see that left hand side is corresponding to H, which is a magnetic parameter. Right hand side corresponding to J is the electric parameter. So you have the magnetic parameter in the XY plane, but the electric parameter is along the Z. Similarly, if we consider the curl of magnetic field in XZ plane, then curl XZ plane will be equal to JY AY cap, and curl H in YZ plane is equal to JX AX cap. Okay. So by definition of curl, H is represented as just del cross H, because by definition we know that curl H can be written mathematically as del cross H. That is nothing but, from the above you could write it as del cross H is equal to JXAX cap plus JYAY cap plus JZAZ cap. So this together on the left hand side, on the right hand side, that together you could write it as just J vector. So therefore curl of H is equal to J vector. It means that, read this statement, it means that the curl of magnetic field is equal to the electric current density. So we have a relation here between magnetic field and electric current density. So this is the speciality of Ampere's law. Fine. Next, let us understand the divergence of vector field. D vector, that is a D vector. Okay. So consider here P, point P in the figure. You consider a point P in the region with charge density rho v. Let ds be the elementary surface area around P and D is the electric flux density. Then it simply means that del dot D vector is equal to rho v, and that is nothing but Maxwell's first equation. Okay, how do you read it? How do you state that? That is nothing but charge density rho v through the surface area ds is equal to the outward flux density d of electric charges through the same surface area. Okay, so that means whatever you consider here in the surface in this area, the charge density passing through this is equal to the outer flux density of the electric charges through the same surface area. So outer flux density is nothing but the divergence of D vector. Next, let us go for one of the important theorems, that is Gauss divergence theorem. Let us see its statement first. The integral of the normal component of the flux density over the surface in an electric field is equal to the volume integral of the divergence of the flux throughout the space enclosed by the surface. It means surface integral of d into ds is equal to the volume integral of del dot d dv. So that means it is a relation between, it's almost a relation between the volume density, integral and a surface integral. Okay, so this is the statement. Now the proof. Again consider the Gaussian surface similar to here, the previous ones. So here also you consider a delta Q be the charge within the differential volume element delta V. Consider that the charge distribution is different in different volume elements within the surface. Then charge density rho v within the closed surface can be represented as mathematically limit of delta Q over delta V as delta V tending to 0. So charge density rho will be limit of delta Q divided by delta V as delta V tending to 0. But what is that limit? Limit is nothing but the definition for a differentiation. So differentiation is nothing but dq by dv. So rho v is equal to dq by dv. So that if you just rearrange, you can write it as dq is equal to rho v into dv. Let it be equation 1. So if q, capital Q, is the total charges present in the entire Gaussian surface, then integrating equation 1, we can write Q, capital Q. That is nothing but integrating means integration of dq is equal to integration of rho v dv. That let it be equation 2. Okay, in the next slide also I have written equation 2. Because now consider Maxwell's first equation, which is nothing but del dot D is equal to rho V. So substitute this equation 3 in equation 2. So that means what you have there is Q is equal to integration of del dot D into dV. Let it be equation 4. By Gauss law of electrostatics, in a Gaussian surface, total flux over the entire surface is equal to the total charges enclosed within the surface. Okay, that also we know. So that means in the surface integral, d dot ds is equal to q. By equating equation 4 and 5, because we could equate, because both of them represent q, capital Q, then we get surface integral of d ds is equal to volume integral of del dot d into dv. Hence the proof. This relation is nothing but Gauss divergence theorem, or just the divergence theorem. We are now looking into another important law, that is Biot-Savart law. It is often referred as a modified version of Ampere's law because, as you remember, previously it was Ampere who introduced the connection between electricity and magnetism. Here, in Biot-Savart's law, it goes one step further, that with the help of this law, magnetic flux density can be calculated at a point or space around a current carrying conductor. That means a current carrying conductor is going to be there. Maybe we consider a red line here in the figure. In the figure, if you consider the red line is a current carrying conductor, and at P we are going to find the equation for the magnetic field. Okay, now refer the figure. In the figure, you see that a current carrying conductor XY is going to be there. Draw a tangent MN. Draw a tangent MN here. Draw a tangent MN at a point O. At a point O in XY, and let dl be the length of differential element of O. Let P be a point. Let P be a point at a distance r from O. That means OP is equal to r, and OP makes an angle theta with MN. Okay, according to Biot-Savart's law, the magnitude of field intensity at a point P due to current in differential element is directly proportional to the length, proportional to the product of the current I, length of the differential element dl, and sine of the angle between tangent drawn to the element and line joining from the point to the differential element, that is sine theta, and is inversely proportional to the square of the distance between the point and the element. Let us introduce a proportionality constant k to the equation, and that k, let it be 1 over 4 pi. Of course, we don't have a much derivation for this in your syllabus. Okay, now substituting this 1 over 4 pi as a proportionality constant, we get dH is equal to I into dl into sine theta divided by 4 pi r square. So as per the law, the direction of dl at P is perpendicular to the plane containing the tangent and line OP. It is directed along the progress of right hand screw turned from dl to the line joining the differential element and the point through the smaller angle between them. So in vector notation, Biot-Savart's law can be written as dh vector is equal to I into dl vector cross ar cap divided by 4 pi r square, where ar cap is the unit vector directed from the point O towards P. To have a feel of the Biot-Savart's law, let us work out one problem. It's interesting. I'll read the problem. A coil of mean radius 8 cm having 100 turns carries current of 10 amps. Calculate the magnetic field produced at the center of the coil and at a point in the axis at a distance 4 cm from the center. Now let us gather the data that is available in the problem. The data are, one is R, that is the radius, 8 cm converting into SI unit, 0.08 meters, number of turns 100, current 10 amps, and length, that is 4 cm or 0.04 minutes. Okay, now from the Biot-Savart's law, what is that we have? We have the equation for dH. So dH is equal to k into I dl sine theta by r square. Let it be equation 1. And also recall the fundamental equation. P is equal to mu naught h, where mu naught is 4.10 to the power minus 7 Henry per meter. And now we will replace that to the above equation. Then you get B vector is equal to I dl sine theta over r square into 10 to the power minus 7 Tesla. That let it be equation 3. So here dl is that length. To estimate the length is nothing but 2 pi r into n, because what is 2 pi r? 2 pi r is nothing but the perimeter. It's a circle. You can see it in the figure. It is illustrated in the figure. As soon as you write the data, it is better you draw the picture so that you understand physically what it is. Okay, so dl will be, by this calculation, is going to be 50.265 meters. Okay, and now from this geometry, from this simple geometry here, distance between O and N can be calculated as r, small r, is equal to root of r square plus x square, which if you calculate will give 0.0894 meters. Now let us estimate the point at a distance 4 cm. So that means it is where? It is at M. Sorry, it is at N. It is at N. It is a 4 cm at N. Okay, here we need to calculate the sine theta because we need to substitute that in the formula. So sine theta at this N is equal to r by root r square plus x square, that is equal to 0.08 divided by root 0.08 square plus 0.4 square, that is equal to 0.894, and r square, if you calculate, that will be equal to 0.008 meter square. So therefore, magnetic field produced at N, using the formula in the previous slide, we can calculate B at N as 5.6 millitesla. Okay, now after one of the parameters calculated, that is at a distance 4 centimeter, now we need to calculate at the center, that is at M. That is at M here. Okay, here. So here again, sin theta is equal to just r by r is equal to 1 in the simple geometry here if you consider, and r square is equal to nothing but capital R square is nothing but the radius there, that is equal to 0.0064 meter square. Therefore, magnetic field produced at M, by using the formula, we get 7.8 millitesla. So we have the equation for the at a distance N, the calculated value at a distance N as 5.6 millitesla, and at the center we have 7.8 millitesla. Okay, let us have one homework here. It is similar to the previous problem. Please work out this and try to get the answer for the problem.